Hello, class. This recorded lecture, again, in section 9.2, hypothesis testing, where the standards or the population standard deviation is known. And we talked about z-score comparisons to either reject or do not reject the null hypothesis. And now we're going to do what's called the p-value calculation. And this is what's typically done now because of the use of technology. It makes it quite a bit easier. And the idea is to calculate the probability of the tails and compare it to a figure of merit. And typically the figure of merit that we compare it to is 5%. So if the value is greater than 5%, you typically say you do not reject. And if the value is less than or equal to 5%, you typically reject. And the smaller that p-value is, the more confidence that you will have that the hypothesis that you're rejecting is actually valid, right, with regard to that. And so the significance level has an effect as well. So let's walk through a calculation or two here, probably two of them. And so the idea here is that we're going to walk through the same one we did in the z-score testing. And this was a SAT prep class. And the claim that the SAT prep class gives you a better performance than if you just didn't take the class, right? And so the way we set this up was we had HO of 530. That was the mean that we were worried about, and we wanted to be greater than that. So our H1, which is our alternative hypothesis, is greater than the standard mean. And what we did here is we knew that the standard deviation was 116. And we also know that we took 100 students that did the prep, and their mean was 600 or 562, excuse me. And you remember we calculated the z-score, and we had a z-score, I believe, of 2.76, I think it was. And we compared it to the 5% tail, which would have been a z-score of 1.645. And you saw that it was much greater, so we rejected the null hypothesis. So the idea is similar, but now we want to calculate a p-value. And when you look at this, we're going to be calculating this p-value here because it's a right tail test. So how do we calculate that p-value? Well, it's because we're going greater than, right? We're going to the right. It's going to be 1 minus the norm dot dist calculation. And when we set that up, it would be 1 minus norm dot dist. And when we do that, remember the x value in this case is going to be our calculated mean from the 100 students, 562, our mean of 530. Our standard deviation, again, is our central limit standard deviation, so it'd be 11.6. And remember, we always do true here. Now, you can do the same calculation with your calculator using the normal dot CDF, I believe. So let me just do this on the spreadsheet for you. Okay, let me pull up the spreadsheet. There we go. You see, I already did it, but let me do it again. So the idea is that it was equals and then 1 minus, and then you bring up the norm dot dist, and that would be 562. That would be 530 for mean. It'd be 11.6 for our standard deviation with the central limit theorem, and this would be true. And you can see when we do that, you get a value even less than 1%, right? 0.0029. And so percentage-wise, that's 0.29%. So when you go back to our whiteboard here, you can see that this value here is 0.29%. And we typically compare this to a 5%. And we're going to call that alpha in our calculation. And if that value is less than our 5%, then we would say that we could reject the null hypothesis. If you wanted a more stringent calculation, you could use 1%, but we still would reject it. So you could see that this has a strong value, right? A strong rejection. You could think about it in that sense with regards to the calculation. And so here we go. And remember, we had the 2.76. And again, that value is just super small with regards to that. And that's the wrong slide. Let me see where. Oh, that is the right slide. Sorry. So here we go. And you can see that that p-value is less than 1%, right? About 0.3% for the calculation. And so again, as we talk about the significance is that if it's less than or equal, we reject. And if it's greater than, we do not reject. And the farther away it is from our set p-value idea of alpha is more significant. And so the typical values that we again use is the 5% value or the 1% value. And if you do 1%, that's a very stringent style of calculation. So we're typically going to do 5, but when you do your homework, make sure you see what value they want you to compare it to. So let's do another example. And this one, I think we've talked about this before. The adult's male average height is 69.7 inches with the standard deviation of 3. And so it says a sociologist believes that taller men may be more likely to be promoted in leadership position. And so basically what they did is the mean height of male executives may be greater than the mean height of the entire male population. So again, 100 male business executives, and their mean height was 69.9. Can we conclude that the male business executives are taller? So when you set up your hypothesis, right, it's going to be equal to mean for the null, greater than, and since our n is greater than 30, we could do this given that we're given the population standard deviation. So again, this is a right tail test. So let's walk through this one again. Try to get the whiteboard up this time. There we go. It must hit all the right buttons. So what do we have here? So we have n equals 100. And the mean that we calculated with 100 was 69.9. Our standard deviation was 3. And the mean that we're worried about here is 69.7. And so our HO is equal 69.7. And our H1 or HA sometimes it is called is greater than 69.7. So we're worried about an alpha of 0.05 or 5%. Okay, so how do you set this up? Well, again, it's a right tail test. So if you think about it, it's going to be this calculation here. So it's going to be 1 minus the norm dot dist. And when you set that up, the point is 69.9. The mean is 69.7, and our standard deviation again is 3 divided by square root of 100, which would be 0.3. Remember, central limit and true. So looking at it, that looks like that number is going to be quite a bit bigger than 5%, but you want to double check with the calculation. And so if we go over to the spreadsheet, it's equals 1 minus and then the norm.dist again. And so to do that calculation, it would be 69.9, 69.7. So the central limit standard deviation was 3 divided by 10, which is 0.3. And this would be true. And so you could see that when you do the 1 minus, you're 25%, all right, 0.25. And so if you take a look at that calculation and you compare it to our alpha level of 0.5, that is much greater, right? Much greater. And so it's not the unlikely scenario that we're looking for. So in this conclusion, we would not reject the null hypothesis. And so if you did the z-score calculation, you could see that the book gives it to you here. You could see it would be 0.67. And if you looked up, comparing that to say the 5% z-score, which was 1.645, again, that is less than that z-score. So again, by the z-score test, you could also say you cannot reject the null hypothesis. So let's do another one. And in this case, I wanted to do one where we had both tails, right? So this is a two-tail arrangement. And you can see that here we have a score test range of 0 to 100. The higher score is greater satisfaction for attitudes working at a company. And it looks like it's 74 with a standard deviation of 8. And so some time ago, the company adopted a policy of telecommuting, which everybody's doing now, it seems like, right? Under this policy, workers could spend 1 day a week at home working. And so this says that they randomly sampled 80 workers and they were given the test for the mean satisfaction, and they wanted to see, and the sample mean here was 76. And assume that our standard deviation is still 8, we conclude the mean satisfaction is different. So if you don't say greater than or less than, different means not equal. So here we go. So let's take a look at this one. So in this case, let's do red on this one. So we have N is 80 workers, yep. And the X mean was 76. And we're comparing it to HO equals 74 and HO or H1, excuse me. I don't know how I got that. Let's try this. There we go. H1 does not equal 74. And so we're assuming that the standard deviation is consistent between both. And so we use 8. Again, N is greater than 30, so we can have that central limit theorem idea when we do this calculation. And you could do the z-score calculation, but what I'm demonstrating here is the p-score. And so the p-score in this case is what is our alpha that we're using? Excuse me, I need to look back here. So we have an alpha of 0.05% or 0.05 or 5%. So here's when you got to think a little bit about what we're talking about, this idea of the two tails. And so the two tails is that we're going to do the right tail and the left tail, all right? And so if we think about the calculation of both of those, with regards to that, we have to take both of these into consideration when we do the calculation. So typically the easiest one to do is the left tail one, right? Because if you think about the left tail, that's always going to give you less than, and it's just the regular norm.dist calculation, right? So that would be norm.dist. And so in this case, you would have 76 for our point, 74 for our mean, 8 divided by square root of 80. And I did that calculation and it's 0.8944. And that would be true. So let's calculate that p-value for the left tail on our spreadsheet. And so the spreadsheet here would be whoops, norm.dist. And you know what? I need the numbers. So let me move this to my other screen so I could actually type the right numbers in. I haven't memorized them. So our X value here is 76. Our mean was 74, and our standard deviation was 0.8944. And we have true. So let's see here. So when we did that calculation there, it is the norm for 76, 74, and that. So I think when I pulled up my whiteboard, I gave you some bad information with regards to this. Here's the other thing that sometimes you need to do the problem to think a little bit, right? So what does this here calculate, right? So this is less than. And so if you think about it, right, here is 74. So what does 76 calculate? Well, 76 is going to be somewhere up here, right? So we're calculating this all the way down. So when we did that calculation, we got 0.98739, which is from this point all the way down. So what would be the upper tail is the easier one to get. So we should do 1 minus that to get the upper tail. So when we go back to the spreadsheet and do the 1 minus, that would just equal 1 minus. You can see it's about 1.26%. So the value that we have here is 0.126%. And so if I go back to here, this would be 0.126% or 0.012. Whoops. Again, getting a lot of little mistakes today. Sorry about that. It's 1.26% or that calculation. And so remember that the beauty of the normal distribution, it's symmetric, right? So if this tail is 0.1026, the left tail also has to be 0.0126. And so remember, if this number is going to be less than and the mean, then you'll be calculating the left tail. If this is greater than the mean, then you're going to end up calculating the right tail. And so if you look at those calculations that the book did, let me pull that up real quick. They showed you here, let's see here. That's still the spreadsheet. Let me pull up this calculation here. And so there we go, found it. Too many files open. And so you can see when they did the z-score calculation and did the measurement from the z-score table, it was real close to what we did on the spreadsheet, right? 1.25% on either side. And so here's how you would do it using your calculator with the z-score test with regards to that calculation. And so what do we do with regards to the two-tail test? Well, the idea in this case is we have to add both of these up, right? So it's a little more stringent. But when you add both of those up, right, it's only 2.5%, right? A little more than if you do the exact calculation than if you use the z-score. But again, 0.0125 or 0.0126 multiplied by 2, right, gives you 0.0250. And you can see that again is half of 5%. So again, you can reject the null hypothesis with regards to that, which would mean that the telecommuting is actually doing, changing the mean of the actual original survey of job satisfaction with regards to it. So that ends this portion of the recorded lecture for section 9.2.